Okay, so we're looking at the derivative graph. So keep in mind, this is not the shape of your original graph. We can create enough indications to help us identify how the graph is going to look. Okay, so we're going to first label this as F prime graph. This is not the shape of the graph. These do not give us the location of the actual graph. These are representing the slope value of the actual graph. So this is a positive slope there, right? Because that's a positive y value. Okay. So to help us know what we're looking at, we like to label our F prime graph. Again, we're on page 3 in our test review packet. Okay. So anything above the x-axis is representing positive slope. Anything on the x-axis is slope 0. Anything below the x-axis is where my actual graph is experiencing negative slope. Okay, so let's first create our F prime sign line. I know it's yeah, so F prime sign line here. This is my slope sign line. I start at -3 and I end at 4. So what can we place onto our F prime sign line? Where do we start with? Yeah, let's find our x-intercepts. These are where our actual graph, original graph, is going to be experiencing slope 0. So places like this, right? So these -2.5, 0, and 2 will look like these points on the original graph. Okay, it'll look like peaks and valleys, and where the actual graph will experience slope 0.
On origin too?
Yeah, origin as well. So we'll say -2.5, 0, and 2. Now, don't look at the rise and fall of the graph. Look at the location. Okay. Is it above or below the x-axis? Okay. What's happening between -3 and -2.5? Below. I know it's rising, but this is to help you remind yourself to look at this and see, okay, this is below, so I'm going to use this marking on my F prime sign line. Okay. What's happening between -2.5 and 0?
Positive.
Above, right? I know it's going up and down, but don't look at the movement here. Look at where it's located. Everything up here, we're going to put that symbol. Between 0 and 2?
Negative slope.
Yep, below the x-axis. And then between 2 and 4?
Positive slope.
Above. Okay, let's go ahead and get the second derivative sign line out of the way, because that's the hardest part. If we can get these two sign lines out of the way, everything else should feel easier.
A lot of same endpoints, being a training for it. From the sun.
Yep, that's right. Endpoints will still be the same. But now we're looking for points of inflection. Now, points of inflection on the F prime graph is going to live where? Max and mins. Yeah,
No.
these are places. These are maximum and minimum slope values. So maximum and minimum slope values will look like this on the graph, right? Imagine you're on a roller coaster ride. Wherever your graph, your ride is going to feel the steepest is going to be point inflection, and those steep slope values that you experience will look like this on the derivative graph. So the peaks and valleys will translate to the steepest places on your graph, which are your points of inflection. So what are the x values there?
-1.
So now we can look at the movement. So now you see how these are all a collection of positive and negative slopes above and below the x-axis, but then the pattern is that these are all slope values that are becoming more positive. So that's going to mean concave what? Up. Yeah. I know it's not shaped like concave up, but again, this is not the original graph, so we don't want to ever say, oh, this is concave down, concave up. We can do that if it's the original graph, but this is the F prime graph, so everything is defined differently. Okay. A negative slope on the F prime graph means concave down. And it's going to keep alternating, right? Positive slope, concave up, negative slope, concave down. So now we're going to sketch the original graph, and I really feel like this is helpful. Cover up your f prime graph. If you're looking at your f prime graph while you're sketching your f of x graph, you're just going to end up copying that graph, and you're never going to be correct if you're creating the same graph for both your function and your f prime. Now there's an exception, but it's not going to be in this case. Okay, so we're going to cover up our f prime graph, f prime graph, and we're just going to force ourselves to look at those arrows to help shape our graph. Okay. We'll start with C first, and then we'll go back to A and B. So we do have some anchor points. So on my F of G, sorry, it says G here. Sorry, I can change my G. Okay, so on my G of X graph, I have some ordered pairs, -3, 3, and 4, 6. So I'm going to go ahead and create that. -3, 3, and 4, 6. And we're just going to follow the direction of those arrows, and our y values may be different from each other, but as long as we're following those arrows, we're good. Now, what do you expect at -2.5 on your original graph? There's a what there?
Change the slope.
Yeah. More specifically, there's a what? Relative minimum. Nice. So now you may be asking, okay, where's relative minimum? Is it here? Is it here? Is it here? It doesn't matter. Okay, so right now you can just target any point you like. Just create some relative minimum at -2.5. And then I'll make my graph decrease until my relative min, and then start rising after that. Okay, and what do you expect at 0? Relative max. Okay, I'm going to target a high point. You don't have to, it can be lower or higher than mine. And then after that, what do you expect that to? Minimum. So I do want it to be lower than this point because I know I have to rise after that. So I do need to make sure I pick a point that is at least lower than that. So 2. And so right now I just care about the slopes. I don't care about the curvature yet. I know this is just the first draft of my graph, but I know that essentially my graph is going to be that. It's not going to look much different than that, except for the curvature. Okay, so now, are we good so far? All right, we're forcing ourselves to just look at this, right? Don't look at your derivative graph. It's not going to help you. So now we're going to go and basically update this graph. We're not going to make much change to it. It's going to pretty much look very similar between this and the end. But we do need to identify our points of inflection. You're just going to identify where the points of inflection is along the path of your graph. You already created the graph, so just indicate wherever the graph lands at -1, then highlight that point. Okay. Everyone may have a slightly different point of inflection, but as long as it's within the correct region within your graph, that's what I'm looking for. Okay. Highlight wherever the graph lands at 1, that's your other point of inflection. Wherever your graph lands at 3, that's your other point of inflection. So you're not creating points of inflection outside of what's already established, right? It's just going to fall along the path. And so now you're just going to retrace the graph. Now your graph will look exactly like the shape that you expect. Right? Concave up, concave down, concave up, concave down, and then the points of inflection are your target points. They will tell you when you're going to start switching back to the other concavity. Okay, so first we're going to start off with concave what? Up until -1. So I'm going to over exaggerate that concavity there. Between -1 and 1, concave down. Between 1 and 3, concave up, and then between 3 and 4, concave down.
Where's points of inflection like there for your space?
Yeah, points of inflection is to help us identify where our concavity is going to switch over, right?
Could you extend it like after the two endpoints too?
No, because our derivative graph ends at -3 and 4, right? We don't have any other information past that, so we're just going to sketch the graph with parts that we have information for. Okay.
Double prime graph.
Yeah, let's do it. I'm going to skip A and B. Hopefully you guys find this pretty easy, right? Because relative max, relative min, concave up, concave down, POI, they're just pulling this from your G prime, G double prime graph, right? That's the easy part. And then your because statements. I'm going to leave that for you guys to try. If you feel like you need extra practice, I have the key and I have all the because statements. So, but hopefully we find this to be the easiest part that I can skip over. It's not asking for a second derivative graph, but I will ask you for the second derivative graph. So let's practice that here. Sorry, I keep saying GF. Now, when you're doing a second derivative graph, you're just going to look at what? Just look at your sign line. Yeah, don't look at anything else. Neither of your graphs will help you out. Okay, sign line is the only thing you need. But it helps to label your second derivative graph. So
still have -3 and 4 again.
Yeah. But I'm going to label my what's above and below. Above means concave up, below is concave down. Anything on the x-axis are my potential point inflections. So where do I start? Yeah, x-intercepts, right? X-intercepts. Where do we want our graph to live to the left of -1 or between -3 and -1? Above. Now, you're just going to make the graph thread between these points. Don't make it match the shape. The shape we've already built, it's going to be for the original function. Okay, so don't force it into the shape that you are hoping for. So above, but these are anchor points, so you know the graph has to reach that point. So I'm going to make my graph look like this. Just a nice and simple graph that lives there, but nothing complicated. Okay. Right. And then how about between -1 and 1? Concave down, so below. So I got to make the graph go below, but it has to come back up. So I'm just going to do the simplest thing I can do and just loop it back up. It doesn't matter how low or how high you go. You just have to make it a straightforward loop because you know it has to come back up. Right. And then between 1 and 3.
Same, but like opposite. So it's like
yep. And then finally,
going down.
Now, we'll say some students get confused because they look at this going, wait, this looks like concave up to me. So why is it concave down? And then they get thrown off because they're trying to match the shape. Don't match the shape, just match the location. And then your graph will be the simplest one out of the 3. Yeah.
You know, like the points of -3 and +4.
Oh yeah, so I can mark that as well. So 3 +4. Yeah. So a good way to kind of double check that you're on the right track here. First of all your graphs look different from each other. Your f of x graph will look the most complex. It has the most changes in direction. And then your f prime graph will be the next one up. And then your second derivative graph will be the simplest looking one. It has the least number of changes. Okay. So that's a good indication that first your graphs will all look different. And then there's an order of complexity. Most complex is your function. Less complex is your f prime. Least complex looking is your second derivative.
For this one, you label it like G prime range.
Yeah. So good. Yeah. Sorry. So g of x, G prime, G double prime. Okay. Let's see. Do we want to do a full optimization problem?
Sure.
Okay. So I did this one in during the help session today, but I'm going to change it up a little bit. So if you already did it in help session, just put it on the separate sheets with different with the different numbers that I'm going to present.
What's this?
Oh yeah, sorry. It's the same process. Yeah. You're just finding the derivative set equal to 0, and that it'll be either the max or min depending on what the problem is asking for. But your problem will look, the exact same setup as this one I'm going to go over with you. Sorry, I'm going to tell you the page here, page 19. Okay, let's change this here. Rectangular storage container has a closed top. And a volume of 10 cubic meters. The length of this base is 4 times its width. So I made some significant changes here, so we can practice with slightly different setup here. Okay, so let me create my box here.
It's 4 times or no, we did in help session.
I think in help session I did 2 times.
Okay.
This is 4 times. So I have information about the base, about the relationship between the width and the length. So if one side is x, then the other side of my base must be what? Or what? X, yeah. I don't have anything about the height, so the height will be its own variable. We know we're going to be optimizing surface area, so that is the equation that we're going to find the derivative for, and then we're going to build in the cost into that equation as well. But let's just get the volume out of the way. That's going to be the supporting equation here. What's the volume of this box based off of these variables?
4 squared h.
Say it again.
4 squared h.
Yeah, 4 squared h. Yeah. So got to multiply all 3 together. Okay. And then we know the volume, right?
It's 10 meters.
10 cubic meters. Yeah.
You recommend like separating out the height like first before you do anything else? So you're just ready for when that step comes?
Sure, you can do that. Yeah, I'm going to wait, but you can do that if you want. Okay, so next, we know that we're trying to optimize surface area because that's going to be associated with the cost. I mean, ultimately, we're optimizing cost, but we know that we're paying for the material, and the material is the surface area, right? We're not paying for the space inside the box. We're paying for the for what makes up the box. So let's build the surface area first, and then we can convert that into a cost equation. Now, think about that word here. There's no need to memorize a formula. You're just going to be creating this from what you know. You're adding up the area of your surfaces. Right? How many surfaces do you have on this box? 6. It's a closed box, right? So that means we got to create 6 area formulas and add them together. Let's start with the base here. What's the area of the base?
4 squared.
It's a closed top, so there's also a top of what? 4 squared. Now, the base and the top has the most expensive material. So I'm going to let that. So we'll separate that from the sides. Now, not all the sides have the same area, right? Let's do the larger one here. This is the larger panel. What's the area of this?
4x.
4xh. Now, if there's a 4xh on one side, there's also a what? 4xh on the other side. Right. How about the smaller side here?
XH.
XH. And if there's an XH, then there's also another XH. So we have 6 surfaces, and each surface has its own area formula. Right? Are we good with that? So we're going to update this into a cost equation now, and we're going to associate a dollar amount for our material. Okay. So the base and the top is going to be the most expensive. How much per square meters?
8x squared.
Yeah, 8x squared times what?
10.
10. Yeah, so we're going to associate that $10 into that material. Okay, what about the sides?
8x squared times 6.
Yeah. So ultimately, yeah, it's going to be 10 times 8x squared, and ultimately here, 10xh times 6. All right, are we good with building each of these parts here to get to our cost equation? Okay, so now our cost is just 80x squared plus 60xh. Any questions so far? So we do want to find a derivative for cost, but something is still unresolved. We would like all this to be in terms of just what?
X.
One variable, right? So this h is what is kind of sticking out here. So we need to find a replacement for h, and that replacement for h is going to come from this support equation that we have for volume. So if I solve for h, divide by 4x squared, right? I can reduce that. 10 over 4 is 5 over 2. 5 over 2x squared. Okay, so that's my h. That will replace that h. And the whole purpose of it is so that we can get this down to one variable and this down to one variable. Then we can move towards getting ready for power rule and then derivative and critical point. So 60 divided by 2 is 30. 30 times 5 is 150. I'm still in the cleanup stage here. I haven't gotten to my derivative yet. One of the x's cancel out. This becomes 150 over x. But this is still not ready for power rule, right? Where does the x have to be for power rule? In numerator.
So you have to do a quotient.
Right, so then we don't have to go through quotient rule, right? Yeah. Anytime we can avoid quotient rule, we would prefer to avoid it. So now it's ready. Now we can go through power rule and set C prime equal to 0.
Put x squared back in the denominator.
Sure, good. So now you're just solving this equation here. Cross multiply, solve for x, and when you solve for x, make sure you go back and read the problem. Is it asking for the dimension? Is it asking for the height? Is it asking for the surface area? Is it asking for the cost? All right, so when you solve for x, it's going to be one of those things. Is make sure that you go back and read the problem and that you're earning as many points as you can and not leaving leaving places where you're going to get points taken off. Okay, so cross multiply here, 160x cubed Let's divide both sides by 160.
Wait, calculator and test, right?
Yeah. Cube root is held under math. So if you click on math, you're going to see that cube root option under 4. And then if you're using your 36 Pro, there's a cube root button here, but you have to hit a 3 first, and then you can hit that. So 3. 0.978 meters. So I know that is one of the dimensions, but it's not asking for the dimension, it's asking for the cost. So I got to take that X value and insert into any of the cost equation that you're seeking to. There's all these different variations. If you want, just choose the one that feels the easiest. Maybe this one here without the negative exponent. Okay, so your problem will virtually look exactly like this on the test. It's just maybe instead of closed, it could be open top. Instead of 2 times, it could be 3 times. And then the numbers will be different, but the structure will be the same. So if you know how to do this, you should feel good. You should know what to and how to study for your test.
In future units, we have to do like other types of optimization.
I'm sorry?
In future units, we have to do like other types of optimization.
No, I'm just going to focus on this one. Tomorrow, I want to do some more practice with from the test review, maybe some mean value theorem, maybe some second derivative graph, and then we'll do some more curve sketching. Okay. No help session tomorrow, but my help session will be Friday at 7:15. All right, come get your phones.
Just said maximum, like define the maximum surface area, and then that would just be like, how do you know that's if this is minimum?
Because it says, because we're trying to minimize costs, right? We're never going to be maximizing cost, right? Just it doesn't make sense for the problem. So whatever the problem says, we never have to worry about, oh, I got to do a different process for, because there's some things that should never work, right? We're always going to be maximizing volume. We're never going to be minimizing volume. So whatever the scenario is, the max and min can only go one way. Yeah, so, but your steps will be the same. You're just finding critical points, regardless of whether you're finding max or.
I don't think I've showed you Friday's work.
Okay.
Great. 29, and then
Okay.
here's page.
But better at auto.
Are you caught up? Everything you, okay, thank you.
Like. Yeah, so then we go through this, but.